We'll look into self-organization in pedestrian crowds. We'll look also a bit into large-scale simulation of pedestrian crowds. We'll look into crowd disasters. Density and flow are surely important, but wouldn't the dynamics be much more interesting? I was actually going out into the field in order to observe people. And here actually some photos that I took at that time. And basically there is a segregation or separation of opposite flows of movement. And that happens even though there's no traffic signs demanding that. There's also no laws requiring this. There are no policemen or women requiring this. It just happens. But the spontaneous emergence of that coordination pattern, this is something that we will be interested in, okay? Then yet what else I noticed, in fact, we might be able, coming from physics, to distinguish different states of pedestrian flows, something like gaseous flow at very low densities, where there would be basically no obstructions, people could move freely with basically no interactions. Then studying at that time, I admit I was sometimes in the discotheque and I was also observing the situation over there and noticed that maybe it's trivial, but the density on the dance floor was much lower than the density of the people standing around. And I thought, oh, maybe that can be actually understood with something analogous to the ideal gas law. So the bigger the speed, the lower the density, basically given the same pressure. That's the overall idea. In fact, I later found another video by Thomas Arns that he captured in front of a cinema. People were waiting for the previous show to end and people to come out. And what you will see is that this flow of people coming out of that cinema will look pretty much like a riverbed, whatever, you know. And now we have two shock waves. One just happened and the second one will just happen in a few seconds. Here, okay? So there's sometimes very abrupt and sudden movements, and that's what we call shock waves. You can imagine that this potentially could be dangerous. In fact, people might fall. There's some pressure in the crowd, you can also imagine, right? And in fact, this can sometimes end in disaster, as it happened during the Love Parade back in 2010. Here, the density was so high that most likely it's more appropriate to compare the underlying dynamics with granular material than with fluids. So there's definitely interaction between the bodies going on, and so forces are being transferred from one body to the next. And as you can imagine, this could be building up a lot of pressure and could be very dangerous. So here's just an intermediate summary of observations. There are gaseous, free, fluid, and obstructed and solid, kind of immobile, more or less, states. Footprints in snow would look similar to streamlines of fluids. Passing through a standing pedestrian crowd leads to river-like streams. In pushy pedestrian crowds, one can observe shock waves. And there are similarities with granular media at very high pedestrian densities. And so the idea was basically to develop gas kinetic, fluid dynamic, and granular models of pedestrian flows. We'll now focus a bit more on emergent phenomena, self-organization, and spatio-temporal pattern formation. And this is really what I was always very much interested in. The fact that the interaction between pedestrians would lead to certain collective patterns of motion without anybody telling them without anybody trying to enforce it or impose it on pedestrians, just based on the local interactions between pedestrians, certain kind of patterns emerge. And among those patterns are what we call the lanes of uniform walking direction, or lane formation. And here is another photograph, this time from Great Britain, obviously. And this is something that we'd like to understand better and to model in a computer. And we also did quite a couple of experiments. You can see over here, there are different kinds of bottlenecks. There are short bottlenecks and long bottlenecks. On the one hand, there are bottlenecks that are being passed by pedestrians walking just in one walking direction. There are bottlenecks that are being passed in opposite directions. And over here, for example, you can see that at bottlenecks, there is an oscillatory flow. That means it's not that those bottlenecks are passed one by one coming from one side, the next one coming from the other side, and then back. But typically, there would be bunches of pedestrians, groups of pedestrians passing the bottleneck, and then the flow direction would turn, okay? Another phenomenon which is quite typical is the pressure principle. So the metro arrives, and then the density inside the metro is typically larger than outside. In other words, also the pressure would be larger, and that's why typically first the metro would be discharged before then people would try to get in. Now, there are also obviously widenings that could matter. In fact, surprisingly, to some extent, a widening has a similar effect than a bottleneck, right? Because people are somehow using that extra space, and then they need to get in again down to a smaller diameter. The other thing, of course, are intersections. So that's what's shown as experiment 4. And here is actually a recording which shows like how surprisingly efficient people are at passing a crossing flow. So we'll see that quite rarely people have to stop. Most of the time they can just walk through this other stream of pedestrians. Something quite surprising, I would say, something that obviously shows emergent pattern formation in space and time, okay? So here is another summary. So people form collective patterns of motion, lanes, oscillations, or stripes. The collective patterns of motion are culturally dependent. There's a preferred side of walking, there's certain acceptable distances and so on. The patterns tend to be quite efficient at normal densities. And this reminds to some extent of the principle of Adam Smith's invisible hand. And we call this also self-organization. That we can understand many of those phenomena that we've seen before based on a physics-inspired model, not assuming any psychology or sociology, such as social norms or whatever, right? Now, how does self-organization, how do collective patterns of motion then come about if it's not social norms? And here just a number of the perhaps most famous models that have been developed in the past. So if you need to come up with a different model for each different situation, then such a model is not very powerful and predictive, while a model that can describe many observations would actually be a lot more powerful, right? Okay, and we'll now focus pretty much on the social force model. this is physics inspired. It basically assumes that people at young age would learn to walk in response to their environment and to other people, and eventually would try to do it better and better. And then the best behavior that they figure out would then be kind of automated. And that automated behavior, optimized behavior, can then, that's the assumption, be approximated by mathematical equations. And in this case, there is an equation of motion, which basically says the change of location with time of pedestrian alpha is given by its speed. And there is an acceleration equation that describes the change of velocity in time. And this is assumed to be approximated by a sum of different forces that describe different influences and effects and motivation. So, for example, pedestrian alpha would want to go with a certain desired speed v alpha naught into a certain desired direction of motion e alpha naught. So we're talking about this term over here. And it takes a certain time tau alpha basically to accelerate. It's actually less than a second typically. So that was this observation that one of the students referred to as no inertia, right? Almost no inertia. And then there are interaction forces, typically repulsive forces between pedestrians to keep some distance and avoid collisions. Obviously, however, there could also be attractive forces such as family members or friends or a tourist group works together. And there could be interactions with walls and with shop windows and whatever. Okay, so all of these forces are then added up to specify the acceleration or deceleration. That's the underlying idea of the social force model. It's something to experiment with, and turns out that this approach is surprisingly successful, and that's why it got cited thousands of times, actually. Right, now here's a breakdown of the interaction forces into psychological repulsion, physical interaction, attraction between people. We've also added a fluctuation term in order to account for random variations and also differences from one person to the next. And now one can simulate those equations. And this is also what we've done. Actually, to be honest, when I started the pedestrian modeling in simulation, there were basically no pedestrian data. We basically had to look into computer simulations and judge whether the outcome that we saw reminded more or less to the qualitative observations, stylized facts, as we sometimes say. Now, there are different ways of fitting models to data. One of them is model-driven, and one of them is data-driven. What I am showing you here is the model-driven approach. Would make certain assumptions about the interaction forces. In this case, the repulsive force would be given as gradient of a repulsion potential. And there would be different specifications. In particular, what I'm showing you here is two different elliptical specifications, taking into account the size of the step of a pedestrian. That means considering that the pedestrian would move forward, also called stride. And there are some parameters in here, such as delta t, for example, that need to, and A and B that need to be adjusted, right? And over here, we are focusing on A and B, and we've also looked into a circular model. And we have additionally looked into a model with an additional parameter lambda, which considers that people are not seeing their environment symmetrically or 660 degrees or 360 degrees around them, but they would basically see the situation in front and respond to it more than to what happens on the side or even behind them. That's reflected by the parameter lambda additionally, okay? Now, the main point about this calibration with a genetic algorithm was that we started with certain parameter values, and then we were with some random mutation changing those parameter values and basically figuring out whether that increased the goodness of fit or also fitness. And what is typically done is that for each pedestrian in a video recording, you would try to predict the location in a second's time away. Okay, so 1 second later. And then you would compare the simulated location with the actual location, and that defines an error, and you would square that error, and you would add up all the errors for all the pedestrians, and you'd try to minimize that overall error by the choice of the model parameters, right? And then those parameters that minimize the error would be the best fit, and that's the parameter values that you would work with, okay? And then in a second step, you would want to validate the results. And for example, you would want to predict the shape of the fundamental diagram, I mean, flow density relationship. And as you can see over here, it worked not perfectly, but kind of reasonably well, up to 3 persons per square meter at least, and there's some deviation.